Hi class, we are now starting chapter 11. This is 11.1a. We're going to be looking at concentration, percent, and fraction. So when sugar is added to coffee, the sugar dissolves. That is, the sugar particles disperse throughout the coffee, forming a homogeneous mixture. This type of mixture is called a solution. The substance that dissolves, for example, which is the sugar, is called the solute. The liquid in which the solute is dissolved is the solvent. The solvent is the major component of the solution. So in this case, sugar, there's not as much sugar, so the sugar would be the solute. And there's way more water, or liquid in this case, that's going to be called the solvent. And that makes up a solution. So a solution is made up of a solute plus a solution. The amount of solute that is present in a solution is its concentration. If a solution contains a small amount of solute, we say it is dilute. If it contains a large amount of solute, we say it is concentrated. A solution that contains a maximum amount of dissolved solute is saturated, meaning no more of whatever it is that's added will be dissolved. It's hit the max amount of what can be dissolved. Okay, so ways to describe concentration. There are several ways to describe concentration, and each have different applications. Ways of describing concentration include by percent, by fraction, and molarity. So in this section, we're going to discuss the first two, and molarity we're going to discuss in the next section. We frequently describe solutions by the percentage of solute present. One way to do this is percent by mass. The percent by mass, or mass percent, is equal to mass of solute over mass of solution times 100. Since both components are measured by mass, meaning grams in most cases, this is sometimes labeled as percent and then mass over mass to let you know those are the units that you're going to use. More commonly, we express concentration by percent by volume. And this is volume percent is volume of solute over volume of solution times 100%. Since both components are measured by volume, this is sometimes labeled as percent and then V over V, which means volume by volume. We often use percent by volume when both the solute and the solvent are liquids. For example, instructions for cleaning might call for a 5% volume or volume by volume solution of bleach in water. In this solution, the solute accounts for 5% of the total volume of the solution. We can prepare the solution by adding 5 mils of bleach to enough water to make 100 ml of solution. So now let's do a problem. A cleaning solution contains 2% volume by volume of ammonia in water. What volume of ammonia is needed to prepare 10 liters of the solution? So we want to set this up. So we recognize that 2% is equal to the volume of solute over 10 liters times 100. So written differently, we could say that 0.02 equals the volume of solute over 10 liters. We can rearrange this equation to solve for the volume of solute, which equals 0.2 liters, or we can write 200 mils. So if this seems confusing, and where do they set this up? Look at the standard equation. Volume of solution, volume of percent, volume of solute. So for this problem, it's asking for 2%. So that's where this one's set up. Remember, the bottom one, I went too far, is volume of solution. So it's asking for 10 liters. That's where the 10 liters of solution. Now all you do is you solve, you basically isolate volume of solute, and it tells you how much of the volume of solute you would need. So use the equation, excuse me, I can't clear my throat. You use the equation to plug in where things need to go, and then you solve for the one that you don't know. So this is not as complicated as maybe it first looks. You just got to understand the equation that goes with it. When a solute, so we're going to look at concentration percent by mass and volume. When the solute is a solid, we often express concentration by mass per volume percent. Mass over volume percent is mass of a solute over volume of a solution. So mass is one unit, volume is another unit. That's where you see grams per mil right there. We write this as percent over mass over volume and frequently use units of grams per mil. For example, normal saline solution used for IV fluids is 0.9% mass per volume. This means that 0.9 grams of salt are present per 100 mils of solution. So normal saline has a salt concentration of 0.9 mass per volume. Seawater has a higher salt concentration than normal saline. Typically, seawater has a salt concentration of about 3.5%. This is still far from saturated. In the Middle East, the Dead Sea has a salt concentration of approximately 34% mass per volume. All right, so let's look at a problem. Normal saline solution is 0.90% sodium chloride. That's grams per mil. How many grams of sodium chloride are needed to prepare 0.50 liters of normal saline solution? So recall that a percentage is a fraction out of 100. So remember, we're using percentages. These are out of 100. And in this case, how many grams of so therefore, if a solution is 0.90% grams per mil, that means that you have 0.90 grams per 100 mils, or 0.9 grams per liter. Okay, so with this one, it was 0.9 grams because it's grams per mil. So this is 0. You just change the percent to grams. You change the bottom one to mils. That's 100 mils. And then what they did here is, remember, 1,000 milliliters equals a liter. So how do you get that? You times this by 10 and you times this by 10. And that's where you get the 9 grams per liter. To find the total mass of sodium chloride needed, we multiply the volume of solution that we multiply the volume of solution that we need by the ratio of grams to volume. 0.5 liters times 9.90 grams per liter. I don't my throat all of a sudden. Okay, let me start again. 0.5 liters, which is in the problem. I don't know if I actually finished reading the problem. How many grams of sodium chloride are needed to prepare 0.5 liters of normal saline solution? So that's where the 0.5 liters comes in now. So this, going over this, they changed it out of mils to liters so we can set it this one and cancel the liters out. So this ends up giving us 4.5 grams of sodium chloride. So that's the amount that would be needed to prepare this much of a solution at this percent. A different approach to this problem is to set up a ratio. And a ratio is 9 grams over 1 liter. So we take this problem, we set it up here, and we solve this as a ratio. And then you have the one that you want. So the units have to be the same, whatever's on top and whatever's on the bottom. I tend to do a problem like this. I learned this when I was doing an internship at Caltech, and they showed us how to do ratios, and it's pretty easy and straightforward. So you know that you're going to have a solution that's this, but you want to make it, maybe in this case, it's going down, right? So you should pay attention to the fact that this is 9 grams per liter. This is half of the liter, so you expect the grams to be smaller than this amount. And that kind of helps you determine if you're doing things on the right track. So you solve for X, you isolate everything, and it still comes out the same as 4.5 grams. We often need to describe the concentration of very dilute solutions. We commonly encounter this when discussing water quality. Of course, clean water is vitally important. Toxic substances in the water supply can cause widespread health issues or have drastic effects on ecosystems, even when they're present in very dilute quantities. For example, pharmaceutical compounds, cosmetics, pesticides, components of plastic containers often find their way into rivers, streams, and reservoirs. These pollutants can endanger the wildlife and humans who drink them. Because of this, government agencies and watchdog groups closely monitor the level of pollutants in lakes and streams. So for many pollutants, even very dilute concentrations can cause environmental and health problems. For example, a group of compounds called polychlorinated biphenyls, or PCBs, were widely used for many years. Although their usage is more limited today, runoff from landfills still contaminates water supplies. According to the U.S. Environmental Protection Agency, the maximum allowable concentration of PCBs in drinking water is 5 times 10 to the negative 4 milligrams per liter. So what that means is that there has to be that much of amount in milligrams only per every liter. That's the acceptable amount that's allowed. That's the max amount that's allowed. So we're going to now look at parts per million and parts per billion. We often express very dilute concentration in parts per million, which is ppm. or parts per billion, which is ppb. For example, if a pond contains 1 gram of nitrate for every 1 million grams of solution, we describe the concentration as 1 part per million, or 1 ppm. Mathematically, we can calculate the parts per million using the following relationship. So we can take concentration of ppm, and this is equal to the mass of the solute over mass of the solution times 10 to the 6. Even smaller concentrations are expressed using parts per billion, or ppb. The relationship is similar. It is mass of solute over mass of solution times 10 to the 9. When calculating ppm or ppb, any unit of mass may be used, but the units for solute and solution must be the same. By definition, 1 liter of pure water at 4 degrees Celsius has a mass of exactly 1 kilogram. Under these conditions, 1 parts per million means 1 milligram of solute, right here, 1 milligram of solute per liter of solution. Similarly, 1 parts per billion means 1 microgram of solute per liter of solution. So what this is saying is that you can convert this to this and use this as a conversion, and from this to this and use this as a conversion, which we'll do. Okay, so let's look at a problem. In a recent study, scientists found that samples from a European wastewater treatment plant contained about 45 micrograms of phthalates per liter of solution. And when you're trying to say this, don't try to say the P and H, say the TH, so phthalates. The pH is there to confuse you. What is this concentration in parts per million in parts per billion? Assume the density of solution is the same as water. So basically, it is, here's the solute. So we have 45 micrograms, which we can then break this down to 45 times 10 to the negative 6 grams. If you look at the conversion on the metric, you'll see that this is what this one means. And then a solvent is 1 liter, which is 1,000 grams. Remember, the units have to be the same so they can cancel out. So in this case, what they did is they transferred this to grams out of micrograms and then plugged in that 10 times 6, which is showing here. And then we can put it into parts per 0.45 parts per million. Because if you solved it like this, it equals parts per million. Now, if we did the same thing with parts per billion, it's 10 to 9, which they have here. They solve for it, and it's now 45 parts per billion. This may take a little bit to get used to, but just follow the solutions and the equations, and remember that this one, parts per million, equals this, and parts per billion equals this. And this is another one you can use instead of this. We have a problem to do. So here is a summary. You have mass percent, volume percent, mass by volume percent. This tends to be grams per mils. Usually it's 100 mils. This is mils over mils usually, and this is grams over grams usually. And then we have mass of solute, mass of solution for parts per million times 10 to the 6. This one's 10 to the 9. And then I just found the page again, so I put it. So let's take a look at these problems. A solution is made by dissolving 5 grams of sodium chloride in 85 grams of water. What is the mass percent of sodium chloride in solution? So I want to point out something that didn't show up in the lecture. It said it, but it said it really vaguely, and I don't think it did a good job, and I caught it after, unfortunately, when I was doing the lecture. So solute and a solution. So when you do that, I'll go all the way back. So when you're talking about solute and solution, the mass of solution includes the mass of solute, because I think when I was discussing it, it's up to whatever I had used as an example, it's what up to the mass is. So in this case, you have to add the mass of solute plus a solution. A solution is solute plus a solvent. That makes a solution. So the solution is solute and solvent. So if that doesn't make sense, let's look at my example. So this is saying a solution, solute and solvent, is made by dissolving 5 grams. So this is a solute, excuse me. This is the solvent. This is bigger. However, a solution is made up of both of them, so we need to add this and this on the bottom. If you did just this, it would be wrong if it's a solution. So the 5 grams is on top, 90 is on the bottom, times 100, and it gives us 5.55, and then we round with the correct, actually, I forgot the zeros. It's 3 sig figs. So this should have another zero on these. I apologize. It's B. So solution, solute plus solvent makes the solution. Both have to be added to the bottom. 1 liter of bleach is diluted with water to form 6 liters of solution. What is the percent by volume of bleach in the diluted solution? So what you got to do here is it's asking for the percent, right? This is volume by volume. So this is, here in this case, it's saying that this is 1 liter of solute. So why do I only have 6 liters on the bottom and not making this 7? Because it's saying this formed 6 liters of solution. The solution total was 6 liters. If it had said it was added to 5 liters of water, then I would have had to add this one plus the 5 liters. But it gave me the total of solution. Solution is solute plus solvent. And that's where this one came in. So this is the volume by volume percent. And this gave me 16.6%. It's 17. These are kind of hard to learn in the beginning, and then once you realize that the equations don't ever change for them, it's not, you just have to kind of translate it. They're not that difficult. In the beginning, it seems a little overwhelming. The Dead Sea contains 34% mass by volume of salt. What volume of salt water from the Dead Sea contains 10 grams of sodium chloride? So in this case, you are going to use the percent, and this is where people get confused with percent. Remember, percent means out of 100. So this is telling you the units that have to be used, and you can flip it any way you want to. So if you have 10 grams, then this means that the mass is 34 grams out of 100 mils. Where did the mils come up from? Because it's volume. And I think I mentioned it's usually always out of 100 mils. If it's not, it's got to be 100 liters, and you're going to have to change the units for this to adjust everything. So when you're doing these, it always tends to be 100 mils. So you adjust it. Grams are on the bottom, 100 mils is on top, and you're going to need 29.4 mils in order to contain 10 grams of sodium chloride. Okay, an assay of tap water from Porterville, California indicated that a sample contained 35.5 micrograms of nitrate ions per liter of water. What is the concentration of nitrates in the water sample? So I gave you the conversion because this is what we're going to use. And now we're just going to pull that out. So if we have 35.5 micrograms, so remember 1 part per billion is 1 microgram per liter. So if I have 35.5 micrograms, and that's per liter, I actually have it in the correct units already. I just got to change it over. So when you plug it into the conversion that they gave you or the other units, it actually is already set. So it's 35.5 parts per billion. It's already in it. We just have to use different units. The concentration of nitrate ions in water sample is 25 parts per billion. What is the mass in micrograms of nitrate ions in 8 liters of water? So let's plug this in. Now what do we have? What do we know? We know that 1 parts per billion is 1 microgram per liter. So if we have this, we can change it into, so I changed it here to 25 micrograms per liter. Now it's asking for 8 liters of water. So 8 liters of water, we set that up, and then we use our conversion. And that tells us that we need 200, it has 200 micrograms. That's the mass of nitrate ions in this. Why is the density there? I think they're doing that to mess you up. Or I'm not really sure. I don't know why the density has been added there because you didn't need to use it.